Howdy. This video is on radioactive decays. Radioactive decays are first-order nuclear reactions. Carbon-14 dating is based on a radioactive decay, and it can be used to determine how long ago something died. Potassium-40 and uranium-238 radioactive decays can be used to determine how long ago rocks were formed. Tritium can be used to determine how long ago water was absorbed by the ground. After watching this video, you should understand how radiometric dating works, and that under the proper conditions, it's very accurate. You should also be able to calculate the time that it takes for an isotope to go from one concentration to another, and you should be able to calculate the concentration after a certain amount of time. And so we've talked about 6 nuclear reactions: alpha emission, beta emission, positron emission, electron capture, nuclear-induced fission, nuclear fusion. Now for all nuclear reactions, the sum of the mass numbers product reactions have to be the same, and the sum of the charges product reactions have to be the same. That's how we balance nuclear reactions. Now the top 4 of these are radioactive decays, meaning that they follow first order kinetics. I also want to remind you that if it says emission or decay, it means the radioactive particle is a product. And so alpha emission is the same as alpha decay. It means the alpha particle would be a product. Electron capture is a little bit different. Electron is a reactant. And so the top 4 are radioactive decays, so they follow first order kinetics. Now when we talked about chemical kinetics, we developed these equations for first order processes, and they're only good for a first order process. And so in terms of chemical kinetics, typically write these in terms of concentrations. In terms of nuclear decays, I typically write in terms of N. You can imagine that's going to be the radioactive particle. And so N is the number at time t, and naught is the initial number, and K is your rate constant. And so if you're trying to calculate the concentration at some time or the number of radioactive particles at some time, you'd use this top equation, NT equals N naught times eta minus KT. Now down here, if you're looking to calculate how long it gets to a certain ratio, you'd use this equation, divide both sides by minus K, and you'd get time is equal to minus 1 over K natural log number at time T over initial concentration over initial number. For first order processes, they're independent of the half-life, and after one half-life, you'll have half as much no matter how much you start with. And so if we started with 20 grams in this case, or 20 milligrams in this case, after one half-life, we'll have half as much, which would be 10. After 2 half-lives, we'd have a quarter as much, which in this case would be 5. And after 3 half-lives, we'd have an eighth as much, which would be 2.5. And so for first order processes, the half-life is independent of the concentration. Now if we start with this equation here, we have natural log concentration times T over initial concentration equals minus KT. Now if we're looking at the half-life, then NT over N naught would be equal to a half, and we can label our T half, and so that's our half-life. Now natural log of half is minus 0.693, and so it equals minus KT half. We can get rid of the negative signs, divide both sides by K, and we get that the half-life is equal to 0.693 divided by K. And so often in terms of radioactive decays, it's given in terms of half-life, and to use these equations, we need to determine our K. And so if you have the half-life, 0.693 divided by half-life gives us K. The half-life is equal to 0.693 divided by K. And it's kind of interesting. Each radioisotope has its own half-life. They can range from billions of years in terms of uranium-238 to milliseconds in terms of fermium-244. Typically for the man-made isotopes like fermium, the half-lives are very, very short. And so for isotopic dating, the activities of radioactive isotopes are measured. And so the activity is just the rate of change, how often they're producing the radiation. Isotopes used for the dating include tritium, carbon-14, potassium, uranium-238. We'll see in the next slide a couple more. And so for potassium and uranium, they're used to date rocks. For carbon-14, it's used to date how long ago organic material died. And for tritium, it can be used to date groundwater. And so there's some others, so you can also use rubidium. And so the parent is what you're starting with, and then it's going to form strontium-87. And so it's also going to be used to date rocks. I mentioned uranium-238, uranium-235, potassium-40, and carbon-14. For uranium-238, its half-life is 4.5 times 10 to the 9 years. Potassium-40, its half-life is 1.26 times 10 to the 9th years. And they're used to date very old rocks. Now it's kind of interesting. You should note that once you have a radioactive decay, it doesn't mean that you're forming something stable. You're probably forming something more stable, but sometimes you have a series of decays. And so here we have uranium-238, and it goes through a series of 8 alpha and 6 beta emissions to get to something stable, which would be the lead-206. To determine the age of a rock that contains uranium, geologists measure the ratio of uranium-238 to lead-206. But it is kind of interesting. There's a lot of steps to eventually get to something stable. The yellow lines correspond to alpha decays. The blue lines correspond to beta decays. Potassium-40 decays by electron capture to form argon-40. The rock is placed under vacuum and crushed, and a mass spectrometer is used to measure the amount of argon that escapes. And so the idea is that there's no way argon can be in the rock to begin with because it's a gas. And so all the argon inside the rock must have come from potassium-40. And so if you know what fraction of the potassium-40 actually decayed, then you can actually use it to date the rock. And so moon rock collected at the Apollo 16 landing site was composed of a mineral common to Earth and is dated at 4.2 billion years. The similarity of ages of meteorites, moon rocks, and oldest rocks on Earth suggests that the solar system formed together. The current accepted age of the solar system is 4.54 times 10 to the 9th years. And so for carbon-14, a constant supply of carbon-14 is produced in the atmosphere, keeping the ratio of carbon-14 to carbon-12 in the atmosphere fairly constant. And so it's produced by nitrogen getting hit by a neutron, forming carbon-14 plus a proton. Now, the carbon-14, carbon-12 atmosphere, because there's a constant intake of carbon while alive, living organisms have the same ratio of carbon-14 and carbon-12 as the atmosphere. Once an organism dies, this ratio starts to change. So the carbon-14 is always decaying, but because living organisms are constantly intaking carbon and replenishing the carbon, the ratio of carbon-14 to carbon-12 in a living organism should be fairly constant. But when an organism dies, it's no longer taking in carbon-14, and so you'll see a decrease in the carbon-14 concentration. And so by measuring the ratio of carbon-14 to carbon-12, how long ago the organism died can be determined. And so there's actually, you can compare the technique to knowns. And so based on tree rings, things that have dates on it. And so the line here is the theoretical curves. The red crosses actually correspond to actual data. And so you see the actual data actually falls on those lines. And again, you can get down to about 6,000 years. And so the carbon from the Dead Sea Scrolls gave 12.1 disintegrations of carbon-14 per minute per gram of carbon. How old are the manuscripts? Carbon in living organisms gives 15.3 disintegrations per minute per gram. And so for carbon-14, the half-life is 5,730 years. The rate of disintegrations is proportional to the amount of carbon-14. Remember, we're talking about a first-order process, and so the rate of disintegrations equals K times the concentration of carbon-14. And so it is proportional. And so there are fewer disintegrations per minute for the Dead Sea Scrolls because some of its carbon-14 actually decayed. And so we can go to the equations that we developed for first order kinetics. Here we have natural log concentration times T over initial concentration equals minus KT. Now, if we want to, we can remember that K is equal to 0.693 divided by half-life, plug that in for our K. And if we divide both sides by this, we get time is equal to minus half-life over 0.693 times the natural log concentration times T over initial concentration. Now the ratio of disintegrations is equal to NT over N naught. Remember that the rate of disintegration is proportional to the amount. And so we can plug in the disintegrations of the dead thing that's been dead for a long time, the 12.1, divided by disintegrations of something currently living. And so if we do the math, we actually get 1,940 years. And so that says the Dead Sea Scrolls are 1,940 years old. It's kind of interesting. This is the Shroud of Turin, and it has been alleged to be the burial shroud of Jesus Christ. Using carbon-14 dating, the flax from which the linen was made was shown to have been grown between 1260 and 1390 AD. It's also kind of interesting. Stonehenge was built 5,000 years ago, and that was determined by carbon dating of the organic material left behind by the builders. I hope that helps.